3 million light-years from Earth, there's an entire galaxy spinning in space that we can see with our naked eyes on very dark nights. The Triangulum galaxy is smaller than our Milky Way, but it has something incredible. It's creating new stars at a speed that amazes scientists. While our galaxy makes 1 star per year, Triangulum makes 10 times more. But here's the mystery no one can explain. This galaxy is coming toward us at a speed of 100,000 kilometers per hour. In a few billion years, it will collide with the Milky Way and Andromeda, creating a giant super galaxy. What will happen to Earth when 3 entire galaxies merge together? What will the night sky look like when we have trillions of new stars shining above us? Subscribe to the channel, leave your like and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Have you ever wondered if there's something magnificent and enormous out there, hiding just beyond what most people can see in the night sky? Something that is actually visible with nothing more than your eyes, if you're patient and in the right place at the right time. Just think about it for a second. Way out past the reaches of our solar system, well beyond the hundreds of billions of stars that make up our own Milky Way galaxy, there sits another colossal assembly of stars, gas, and dark matter. That is the Triangulum galaxy, and even though it is unbelievably far away from us, it reveals itself as a tiny smudge of light under dark skies. Its story is one of scale, on a level that is genuinely difficult to comprehend, yet it is a story deeply linked to our own cosmic neighborhood. Let me walk you into what makes the Triangulum galaxy so special. People often refer to it by its catalogue number, Messier 33. That's because centuries ago, the French astronomer Charles Messier catalogued it while tracking down objects that could easily be confused for comets. Messier 33 is located about 3 million light-years from Earth. To be more specific, it rests a bit beyond the famous Andromeda galaxy, but still bound in the same gravitational group as us, what astronomers call the local group of galaxies. When you hear the term local group, it's kind of funny because on the cosmic scale, it's still immense. A cluster of more than 50 galaxies, but the Triangulum galaxy is one of its biggest and brightest. Triangulum owes its name to the constellation it's found in, Triangulum, which is a faint constellation shaped by 3 stars in a modest triangle in the northern sky. If you know exactly where to look, and the night is as dark as it can possibly get, far away from city lights or even moonlight, you might just see it as a small, delicate fuzz, almost like a pale ghost just above Andromeda. That alone is mind-blowing. With no telescope, just your eyes and patience, you're actually looking at light that set out toward us about 3 million years ago. This makes Triangulum one of the most distant objects the unaided human eye can see. Think about that for a moment. When the photons of light that are entering your eye right now left the Triangulum galaxy, the very first humans were just appearing on Earth. That's how far back in time this galaxy is, every time we glimpse it. The Triangulum galaxy is the 3rd largest member of our local group, the other 2 massive ones being our Milky Way and the Andromeda galaxy. While Andromeda is more massive and more luminous, Triangulum holds its own charm. In terms of size, it is about 1/4 the mass of the Milky Way. Now, our galaxy, the Milky Way, contains hundreds of billions of stars. Triangulum, being smaller, probably has something close to 40 billion stars. Still a mind-bending number if you think about how many stars that actually is, each with the potential of hosting planets, moons, and who knows what kind of cosmic stories. Its spiral shape gives it a certain beauty that you'll find echoed in many galaxies sprinkled throughout the universe. But because it is relatively smaller, it is considered almost a junior spiral galaxy compared to its siblings. That difference in size, however, doesn't make it any less fascinating or important to astronomers. In fact, its medium characteristics make it a kind of reference point for studying how spiral galaxies like ours behave, how they are born, how they change, and how they interact with their environment. Now, the specific structure of Triangulum is something astronomy geeks love to talk about. When you look at detailed images from powerful telescopes, the Triangulum galaxy presents itself as a nearly face-on spiral. That simply means we see its swirling disk almost as if we're looking at a pancake from directly above, rather than from the side. This orientation is important because it lets us see its spiral arms very clearly. These arms are not just pretty, they are bustling with activity, especially around star formation, which is a whole other captivating topic microscopic about this galaxy, you notice these bright regions, called H2 regions, scattered along the spiral arms. They're basically nebulas where new stars are being born from clouds of gas and dust. The galaxy isn't cluttered with a big bulge of stars in the middle like we see in Andromeda or the Milky Way. Instead, Triangulum has a smaller central bulge, so a lot of its activity and light comes from those extended prominent spirals. Visibility from Earth really depends on your conditions. For many people living in or around big cities, the sky never gets dark enough to notice anything but the brightest stars or planets. But in the countryside, especially on moonless nights in autumn, the Triangulum galaxy becomes a kind of rite of passage for amateur astronomers. The best time to look for it is usually in the late hours after midnight from September to January. It's a test of patience and vision. It won't jump out at you like the brighter Andromeda galaxy does. If you train a small telescope or even good binoculars toward that part of the sky, you'll see that faint smudge resolve into a patch a few times wider than the full moon. And remember, each point of that dim light is not just one star. There are billions wrapped up in those winding spiral arms. For astronomers, it is sort of like reaching out and touching the broader universe right from your own backyard. The first scientific investigation of Triangulum probably dates back to the mid-18th century. Messier himself marked it into his famous Messier catalogue as object number 33, which is why it's commonly called M33. But its true significance became clear only with advances in spectroscopy and photography around the late 19th and early 20th century. With the development of bigger and better telescopes, astronomers determined that the Triangulum galaxy is not just a fuzzy patch inside our own galaxy, as many originally believed, but an entirely separate system, another island universe filled with its own stars, gas, dark matter, and secrets. Edwin Hubble, in the 1920s, used galaxies like Triangulum to show that the universe is vastly larger than what people once imagined. By studying Cepheid variable stars within Triangulum, stars that pulse in brightness at regular intervals, Hubble was able to figure out how far away it really is. That discovery essentially expanded the boundaries of our universe by millions of light years. Astronomers have always been interested in Triangulum because it represents an excellent laboratory for understanding galaxy formation and evolution. Its structure is relatively undisturbed. It hasn't been as dramatically altered by interactions with other galaxies as some of its neighbours. That makes it a sort of cleaner case for studying how spiral arms form and behave, how star clusters are born and then scatter over time, and how gas and dust contribute to the cycle of stellar life. Even though Triangulum does interact with the gravitational pulls of Andromeda and faintly with the Milky Way, it has managed to hang on to its identity for billions of years. For researchers, every new observation of Triangulum means a little more knowledge about the behaviour of medium-sized galaxies in the universe. In terms of its physical dimensions, Triangulum is pretty big by any normal standards, but on the cosmic scale, it comes off as a respectable but not dominant sibling. From edge to edge, Triangulum measures around 50,000 light-years. To put that into perspective, light, the fastest thing in the universe, would take 50,000 years to travel from one side to the other. Our Milky Way, by comparison, is more than 100,000 light-years across. Triangulum's mass is perhaps 1/4 of our galaxy's, meaning its gravity is strong but not quite in the heavyweight division of cosmic structures. Even so, it's estimated to have at least 40 billion stars, and maybe even more planets, plus huge amounts of hydrogen gas and dark matter we can only infer from its motion and gravitational effects. This vastness is not empty. Triangulum is brimming with objects and phenomena that keep astronomers coming back for more. Its arms aren't as tightly wound as those of some spiral galaxies. They spread loosely outwards, those graceful elongated curves laced with blue-white starlight and knots of glowing red gas. These arms teem with regions where stars are being born at a pace well beyond what we currently see in our own Milky Way. The central region may be less packed than, say, Andromeda, but it's still fascinating. Astronomers believe there is a small, supermassive black hole at the centre, maybe only a small fraction as massive as the monster in the heart of our own galaxy, yet still impressive in its own right. These features give the Triangulum galaxy an energy and character that set it apart, even when compared to its illustrious neighbours. Seeing the Triangulum galaxy on a dark, moonless night can feel like looking through a window into the deeper cosmos. It might not dazzle brightly, but just knowing what it represents makes it pretty special. You stand under the sky, and for a moment you connect with light that's travelled across 3 million years of empty space, a truly ancient signal. Imagine all the history that's taken place since that light set out. The rise and fall of human civilizations, the slow drift of continents, the evolution of life on our planet. Meanwhile, the Triangulum galaxy has just carried on its grand, slow spin, orbiting the center of mass of the local group, continuing its complex story. The importance of Triangulum extends beyond just the thrill of seeing it. Scientists use it as a touchstone for exploring some pretty big questions by comparing its features, its star formation regions, its distribution of gas and dust, its central black hole, and the patterns of its spiral arms. With other galaxies, astronomers get a clearer sense of how galaxies like our Milky Way came to be and how they might act in the future. Because Triangulum is close enough for us to see individual stars and clusters, but far enough to behave as its own island, it provides a kind of in-between view, far more detailed than what we see in much more distant galaxies, but less confused by overlapping stars than what we see looking through our own galactic disk. It's also a galaxy that's, for all its visible beauty, shaped by invisible forces. Like all galaxies, Triangulum is held together mostly by dark matter, a mystery substance we can't see but know is there because of the way the galaxy spins. Astronomers can measure the movements of gas and stars in the outer arms of Triangulum and see that they are travelling much faster than can be explained by the visible mass alone. The conclusion: there must be a giant halo of dark matter that extends far beyond what we can see. This connects it to fundamental mysteries about the substance and fate of the entire universe. Triangulum's relationship with its neighbouring galaxies is subtle but intriguing. For most of its life, as far as we can reconstruct, it has had a somewhat gentle existence compared to galaxies in bustling clusters where collisions and interactions are common. Over millions of years, though, its path and speed have been influenced by the larger mass of Andromeda and, indirectly, the Milky Way. There's evidence it may already have had a close passage with Andromeda galaxies in the past, a twist that helps explain some of the slight warps and streams of stars visible at its outer edges. This kind of slow-motion choreography among the big galaxies shapes not just their future, but the future of our entire corner of the universe. Because it is such a nearby cosmic neighbour, Triangulum provides a key testing ground for technology and methods that will go on to study more distant and exotic galaxies. Researchers use the galaxy to calibrate their instruments, practice their skills in measuring faint glows and mapping out clusters of newly forming stars. Observatories from ground-based giants in Chile and Hawaii to space-based telescopes like the Hubble and soon the James Webb Space Telescope have all pointed their mirrors at Triangulum. With high-resolution space imagery, we can see details as small as a few light-years across, mapping young star clusters, ancient globular clusters, and the delicious swirls of dust and gas that fuel the next generation of stars. By collecting data across all forms of light, from visible to infrared to radio waves, scientists extract clues about how elements like oxygen, carbon, and iron get cooked up inside stars and spread across the arms by supernova explosions. To everyday people, Triangulum Galaxy might sound like something far off and unattainable, but in reality, it is deeply woven into the fabric of our own story. Its light has made it through 3 million years of obstacles and open space to reach our eyes, or our telescopes. It stands as both a challenge and an invitation to see the universe not just as a collection of distant points, but as a place with real, reachable neighbours. For amateur stargazers, the hunt for Triangulum is a small adventure, one that can lead to some of the grandest questions in astronomy. For scientists, it's a laboratory, a neighbour, and a signpost marking our position in the cosmos. When you look up at the sky and perhaps with a stroke of luck spot that pale smudge in the Triangulum constellation, you are connecting with something truly ancient, distant, and extraordinary, a galaxy all of its own, living out its story alongside ours. Triangulum isn't simply another dot in the darkness. It is a vast, living place with billions of suns, swirling and evolving across the eons, and it waits, quietly but firmly present, as a reminder of how much universe is really out there, waiting to be discovered. If you take a closer look at the Triangulum galaxy, one thing that grabs attention almost right away is how incredibly active it is when it comes to forming new stars. After getting a feel for the sheer scope of this galaxy, it's pretty wild to learn that, even though it's smaller than the Milky Way, it is actually way ahead of us in churning out baby stars. That might not be what you'd expect, considering how many more stars the Milky Way already has, but the numbers say it all. While the Milky Way produces around one new star every single year, Triangulum is busy pumping out about 10 new stars in that same stretch of time. For something with just a fraction of our galaxy's mass, this is sort of like seeing a smaller city outpace a huge metropolis in building houses every single day. The secret to Triangulum's speed in building new stars is tied directly to the raw materials floating around inside the galaxy. In its spiral arms, there are huge clouds filled with hydrogen gas and dust. These are the building blocks every star needs at the very beginning of its life. The arms themselves are quite loosely wound, not squeezed tightly into the center, and that kind of open structure seems to help in letting these star factories flourish. When you look at images from telescopes, you'll notice all sorts of glowing patches and knots. Many of those are what astronomers call H2 regions. These are gigantic clouds of gas being lit up by the bright, hot, young stars that are forming right in their midst. Most of the star birth in Triangulum happens exactly in these places. So what actually sparks all this star-making action? First, Triangulum hasn't used up as much of its star-forming fuel as some other galaxies of its age and size. It still has vast reserves of cold hydrogen, which is a key ingredient for making new stars. If you imagine the process, it starts with these clouds of gas drifting through the spiral arms. Over time, pockets of gas get denser and denser, usually set off by the shock waves from older stars exploding as supernova, or by passing density waves that sweep through the galaxy. Some of these areas collapse under their own gravity, pulling the gas tighter until it gets hot and dense enough in the center to start nuclear fusion. That's the official birthday for a star, when fusion begins and the new star starts to shine. There's something else that encourages this fast-paced star creation in Triangulum. Even though it currently looks like it's just calmly spinning on its own, astronomers think that it may have brushed up against, or even passed close by, the much bigger Andromeda Galaxy at some point in its past. A near miss, even if it happened a long time ago, can pull on the gas clouds by gravity, stirring things up enough to trigger waves of starbirth. These interactions don't even need to be dramatic collisions. They can just be close gravitational nudges, which are pretty common in the crowded neighborhood of our local group. This might have given Triangulum that extra push to get its star-forming engines running at this higher speed. Looking closely, the biggest and brightest star-forming region in Triangulum is something called NGC 604. It's one of the largest such regions that astronomers have found anywhere nearby, and it absolutely dwarfs the famous Orion Nebula in our own Milky Way. Inside NGC 604 alone, there are enough massive, hot, young stars to light up the entire cloud and make it glow in that distinctive reddish colour that marks where ultraviolet light is making the clouds shine. This one patch of the galaxy is a real hotspot for new star birth, and it's one of the first things astronomers look at when trying to learn about how different galaxies create stars. The rate at which a galaxy forms new stars isn't just an interesting side note. It has a major effect on how that galaxy changes over time. With Triangulum making about 10 new stars every year, its overall look and contents are still evolving pretty fast compared to a galaxy like ours, which is a bit more settled. Each new star brings along the possibility of forming planetary systems, and many will eventually explode as supernovae themselves, spreading newly made chemicals and stirring up the gas clouds to make way for even more stars down the line. This continuous recycling of material means that Triangulum's future, how it will look millions of years from now, depends directly on how long it can keep finding enough fuel for all this activity. Of course, fast rates of star formation also come with some downsides. All those bright, massive, short-lived stars have powerful winds that can blow away the gas around them, making it harder for more stars to form right nearby. When they end their lives in gigantic supernova explosions, they blast shockwaves that can both trigger new rounds of starbirth and also sweep out regions of gas, sometimes shutting down further star-making in those spots. So while Triangulum's star-forming frenzy is impressive, it's not guaranteed to last forever. At some point, if it runs out of gas, things will slow down, just as has happened in other galaxies. Scientists love to study this galaxy because it holds clues about how galaxies like ours may have looked in the past. In our universe, galaxies tend to start out with lots of gas and dust, forming stars at a wild pace. Over time, as they use up their stockpile of star fuel, or as interactions calm down, that frantic activity tapers off. Triangulum, with its steady supply of star-forming material and its relatively recent bursts of activity, is almost a snapshot of what the Milky Way might have been like billions of years ago. By watching Triangulum, astronomers can get a better handle on the full timeline of galactic evolution. One way researchers measure just how efficient Triangulum is at making new stars is by checking the galaxy's gas-to-star conversion rate. This tells you what fraction of the available gas turns into stars every year. In Triangulum, this conversion rate is high enough that it keeps the cycle of stellar birth in overdrive, but not so extreme that it exhausts the supply in a single burst. Compared to some galaxies that go through violent, short-lived starburst episodes, Triangulum seems to have found a sweet spot, a pace that's both energetic and sustainable, at least on the timescales we can study. When you look at pictures of Triangulum taken in different types of light, you really get a sense of where the action is. In visible light, those pink and red regions stand out as textbook examples of new star formation. But when astronomers look with radio telescopes tuned to the frequencies where cold hydrogen glows, they find big pools of potential star fuel spread across the spiral arms, and even in some zones just outside the arms. Infrared observations, which can see through thick dust, reveal hidden baby stars tucked away inside those gas clouds, just starting the earliest stages of their lives. Each different telescope offers a new way of mapping this frenzy of star birth. All this bustling activity draws researchers who want to answer questions not just about how stars are born, but what that means for the whole galaxy's chemical makeup. Each time a massive star ends its life, it creates heavier elements inside its core and then spreads them out in a supernova blast. Over millions of years, these elements get mixed back into the galaxy's gas clouds and become the raw stuff for new stars, planets, and maybe even life someday. In Triangulum, this cycle seems to be running fast and at a large scale, so scientists can see many stages of this enrichment process all at once. It's like having a lab where you can watch chemistry in action, except the experiments are star-sized and take place over thousands or millions of years. Because star formation in Triangulum is so vigorous, some astronomers use it as a local model for more extreme galaxies much farther away. There are galaxies in the early universe that light up at even higher rates, but they're distant and hard to study in detail. Triangulum, though, sits close enough for telescopes to capture individual clusters, nebulae, and the aftermath of star explosions, giving us sharper insight than most other examples. By figuring out what sparks these bursts of activity, what sets the pace, and how long the show can go on, researchers can fine-tune their theories about how galaxies everywhere live and age. Another question that comes up is how Triangulum manages to hold on to so much of its gas despite all the activity. After all, supernovae and stellar winds can blow lots of the galaxy's material into space, especially in a smaller galaxy where gravity has a harder time pulling it all back. But surveys show that Triangulum actually has enough gas left to keep forming stars at this rate for a few billion more years. This suggests it's pretty good at recycling, or maybe even pulling in extra gas from the outskirts, sometimes by capturing smaller nearby clouds or even by drawing some in from its cosmic environment. This helps explain how it keeps its star-making engine running so hot for so long. The relationship between the spiral arms and star formation is particularly interesting in Triangulum. In many galaxies, those arms are the highways where most new stars get made, and that holds true here as well. The spiral arms are denser than the spaces in between, and they act sort of like natural pressure waves, squeezing the gas clouds as they orbit around the galaxy. As the gas passes through the arms, it gets compressed, and this kick starts the collapse of clouds into new stars. In Triangulum's broad, open arms, there's just the right mix of pressure and gas density to fuel all this continuing activity. Astronomers look for signs of patterns, how the stars are distributed by age along the spiral arms, and use this to reconstruct the recent history and predict what might happen next. The pace of star birth doesn't just affect how Triangulum looks now, it also determines what it will look like in the distant future. The ongoing star formation means the galaxy continues to give rise to new generations of stars, including both massive, short-lived blue stars and smaller, longer-lived ones, more like our Sun. As time passes and the hot, bright stars burn out and explode, their remains mix into the next generation, while the stars that live longer stick around, slowly making the galaxy brighter and more complex. If Triangulum keeps this up for the next billion years, it will gradually change its color and shape as the mixture of younger and older stars keeps shifting. There are also opportunities to study how star formation can sometimes be shut down, not just by running out of gas, but by changes in the galaxy's environment or even by feedback from its own stars. For example, the energy and shock waves coming from clusters of supernovae can blow large parts of the interstellar gas out into space. If this happens on a big enough scale, it could cause the galaxy to drop its star production, at least for a while. By comparing these effects in Triangulum with what's observed in galaxies that are slowing down, astronomers can understand better how the balance of star birth and death drives the broader evolution of galaxies across the universe. With better telescopes coming online, like the James Webb Space Telescope and future observatories, researchers will keep digging into the details of Triangulum's star-forming machine. High-resolution images and data let scientists pinpoint exactly where new stars are appearing, how the gas is behaving around them, and what changes over time. For instance, they can chart the chemical fingerprints of different regions, catching where supernova debris has enriched one spiral arm but not another, or trace how quickly clusters of stars disperse into the galaxy after their nursery clouds are blown away. The closer they look, the more complicated and fascinating the picture becomes. Some astronomers are also interested in how Triangulum's higher rate of star formation could affect its relationship with the other big galaxies in our group. For example, could all this activity add up to make Triangulum more influential during future close passes with Andromeda or the Milky Way? Every new round of stars slightly changes the gravity and mass of the galaxy, which could have consequences millions or billions of years from now, as the orbits of the local group members bring them together in cosmic slow motion. Tracking all this in real time is impossible on a human timescale, but studying Triangulum lets specialists make careful predictions. Because the process of creating new stars goes hand in hand with making planets, Triangulum's higher activity level makes it a tempting place to search for the ingredients of alien worlds. Bright young stars light up their own surrounding disks of dust and gas, and in those disks, new planets begin to form. In fact, regions like NGC 604 could be full of planetary systems just starting out. Right now, we don't have the technology to see planets in Triangulum directly, but by understanding where and how the stars form, we can make some good guesses about where to look in the future. In summary, Triangulum's exceptional rate of star formation really sets it apart from most galaxies nearby. This galaxy hasn't just maintained a steady drive to create new stars, it's doing it on a scale that outpaces much larger galaxies, including our own. Factors like its rich supply of hydrogen gas, its loosely wound spiral arms, and perhaps even past glancing blows with its neighbours all team up to keep this star-making apparatus running at high gear. Every year, it adds about 10 new stars, each with its own potential for planets and future generations of stars. And this cycle is a window into the ongoing growth and change that shape not only the Triangulum galaxy, but galaxies like it across the universe. Researchers will keep watching Triangulum for clues about how long this fast pace can last, how it will affect the galaxy's future, and what it can tell us about the way galaxies work in every corner of the cosmos. Whether the process eventually slows down due to a lack of fuel, or whether some new trigger speeds things up again, Triangulum remains a crucial piece of the puzzle in understanding star formation and galactic evolution as a whole. This constant cycle of new stars springing to life in Triangulum is actually part of a much bigger story, one that involves not just what's happening inside the galaxy, but also how the galaxy itself is moving in space. One fact that a lot of people find surprising is that the Triangulum galaxy is not drifting away from us the way most galaxies across the universe are. Instead, it's gradually heading in our direction. While to us, everything in deep space can seem permanently fixed and unchanging, the reality is that galaxies are always on the move, and their paths are shaped by the gravitational forces of everything around them, especially their biggest and closest neighbours. To get a sense of what's really going on with Triangulum's motion, it helps to look at what astronomers have found by tracking its speed relative to the Milky Way. Based on careful measurements that include the Doppler shift of light, where the wavelength wavelength of light changes depending on how fast an object is moving toward or away from us, scientists have determined that Triangulum is getting closer to our galaxy at a speed of roughly 100,000 kilometers per hour. That is a distance so large and a speed so fast that it's hard to put it into practical terms, but it's absolutely enough to have a big impact over millions and billions of years, which is the kind of timescale we're talking about in astronomy. Unlike many other galaxies which are racing away from us because space itself is expanding, Triangulum is locked in a local tussle of gravity with neighbouring galaxies inside what's called the local group. A lot of folks have heard about the Andromeda Galaxy heading toward the Milky Way and how those two galaxies are on course for an eventual merger. What's less well known is that Triangulum is a significant part of that story. The Triangulum Galaxy has its own trajectory, and its fate is tightly connected to both the Milky Way and Andromeda. In fact, figuring out exactly where Triangulum is going and how it will interact with these larger galaxies is keeping a lot of professional astronomers busy. Digging into the motion of Triangulum, researchers use not just Doppler shifts, but also very fine measurements of how its image appears to move across the sky. This is called proper motion, and it's an incredibly subtle thing to detect at a distance of about 3 million light-years away. But thanks to missions like the Hubble Space Telescope, and even more advanced telescopes coming online, scientists have started to pin down the three-dimensional path that Triangulum is following through space. What they've confirmed is that Triangulum is not just approaching us head-on. Its path is more of a complex dance, orbiting around Andromeda and, to a lesser extent, feeling the pull of the Milky Way and even some of the smaller galaxies and dark matter clumps nearby. Some astronomers think that Triangulum may have had a near pass with Andromeda in the past few billion years. There's some evidence for this in the way both galaxies have some warping and tidal features in their outer regions. That is, their stars and gas are stretched out in a way that suggests a close gravitational encounter. The details are still being debated because the actual paths are tricky to reconstruct when you're talking about events that happened hundreds of millions or billions of years ago. Still, current measurements show that Triangulum is, at this moment, on a broad arc that has it heading generally toward Andromeda, which itself is barreling toward the Milky Way. This sets up the whole local group for a gigantic reshuffle at some point in the far future. It's not just the direction and the speed that matter. Triangulum's motion affects a lot of things, including its shape, its internal dynamics, and its future. As it pushes through space at these enormous speeds, its gas and stars feel the gravity of the other big players, causing subtle shifts and even helping to drive some of the star-forming activity we see today. When two massive galaxies get close to each other, their gravity pulls on the stars and on the massive clouds of gas and dust, sometimes causing bursts of new star formation or even funneling material into the center of one galaxy or the other. In Triangulum's case, recent history may include just such a gravitational nudge from Andromeda. Over the next few billion years, the pull of gravity is likely to make Triangulum's orbit wobble, warp its spiral arms a bit, and eventually draw it closer, not just to Andromeda, but potentially into a group encounter with our own galaxy as well. When astronomers track these cosmic motions, they are essentially mapping out the fate of our tiny neighborhood in the universe. The local group is not just a collection of galaxies floating randomly, it's more like a loosely bound cluster, all tugging on each other as they travel through space. The exact alignment of Triangulum, Andromeda, and the Milky Way dictates how this trio will interact in the deep future. It's not just a question of if the galaxies will meet, but when and how the encounters will happen and what the mergers or close passes will do to the shapes and the contents of the galaxies involved. Triangulum's speed of about 100,000 kilometers per hour is actually calculated relative to our position here in the Milky Way, and it isn't uniform across time. Over the vast ages involved, gravitational tugs can speed up or slow down parts of the galaxy, shifting how quickly it is actually closing the gap. Even the larger structure it's a part of, the local group, is moving together through the wider universe, pulled by other nearby galaxy groups and by the mysterious influence of dark matter, which acts like a giant gravitational web holding everything together. All this motion doesn't just affect the galaxy's positions, but changes their shapes, their star-making histories, and the destinies of the stars and planets inside them. An interesting part of this story is how scientists can use what they know about the motions inside Triangulum to learn about things like the mass of Andromeda or the distribution of dark matter around both galaxies. When Triangulum approaches Andromeda, for example, the way its orbit bends gives clues about just how much stuff, stars, gas, dark matter, is sitting inside Andromeda's invisible halo. Similarly, the changes in how Triangulum spins can signal whether it's being stretched or compressed by these outside forces. Sometimes, astronomers even spot faint streams of stars that seem to be torn off as a galaxy swings by another, leaving long trails that mark the path of past encounters. What's really fascinating is that because Triangulum is on this approach, it sort of stands out against the backdrop of the rest of the expanding universe. Most galaxies, as seen from Earth, are moving away from us because of the overall expansion of space since the Big Bang. This is what's called Hubble's law, and it means the farther away a galaxy is, the faster it usually appears to recede. Triangulum breaks that rule for us because it is gravitationally bound to the local group, and within this group, the gravity between all the members is stronger than the effect of the universe's expansion at these distances. That's why, instead of seeing its light stretched into longer wavelengths as it escapes, we see some of its light compressed or blue shifted, indicating it is coming closer. The story behind the Triangulum galaxy's approach has been pieced together from years of careful observation and advanced computer modeling. Astronomers have drawn on everything from direct imaging to precise measurements of faint starlight, as well as tracking the motion of individual stars and clouds of hydrogen in Triangulum's spiral arms. Some of the best information has come from the Hubble Space Telescope, which is able to detect movements as small as a fraction of a thousandth of a degree per year, even at distances of 3 million light-years. These tiny shifts eventually add up, helping scientists build maps of exactly how Triangulum is moving relative to everything else nearby. A big part of this work involves computer simulations. Researchers use our best estimates of the mass, speed, direction, and position of all the major galaxies in the local group to run virtual models of how these galaxies have moved in the past, how they're moving now, and where they'll go in the future. By tweaking these models to match what we observe about Triangulum, Andromeda, and the Milky Way, scientists can start to predict what will happen over the next several billion years. This isn't guesswork. It relies on the physics of gravity and painstaking cross-checking with actual telescope observations. One question that often comes up is whether Triangulum will slam directly into one of its neighbours, get captured in orbit, or just swing by and keep going. That's still an area of research with a few possible answers, depending on small details like exactly how much dark matter is present, or if there are previously unseen influences nudging the galaxy's orbit. In some longer-term simulations, Triangulum ends up getting grabbed by Andromeda and eventually merging with it. In others, its path winds around the outside for a while, and it gets caught up in the bigger merger between the Milky Way and Andromeda. Whatever the details, the overall trend is that Triangulum is not going to escape the gravitational pull of its big neighbours forever. Sooner or later, in hundreds of millions or even a few billion years, it will become part of a much larger cosmic event. But none of this is happening quickly, at least not on a human scale. Even moving at 100,000 kilometers per hour, Triangulum is still millions of light years away from us, and these kinds of shifts take ages to play out. From our point of view right now, nothing dramatic will change in our night sky for a long time. The stars inside Triangulum will keep forming, living and dying in the meantime, and the galaxy will continue tracing its slow arc through the neighborhood. Another layer of complexity comes from smaller galaxies and streams of material that also interact with Triangulum. The local group is more than just its 3 largest members. There are dozens of dwarf galaxies, clumps of matter, and the large dark matter halos stretching far beyond what we can see. As all these elements pull and push on each other, the path that Triangulum follows gets a little more complicated. Some scientists are looking at evidence that the galaxy may have already experienced smaller collisions or mergers with dwarf galaxies of its own in the past. If so, those encounters could have stirred up the spiral arms, brought in new supplies of gas, or even set off some of the recent star formation outbursts. As Triangulum makes its way toward the heart of the local group, it tilts the balance of gravity in subtle ways. Satellites orbiting Triangulum, or even clouds of gas sitting in its outskirts, end up moving differently as the whole group shifts. When Triangulum passes closer to Andromeda, or eventually heads toward the Milky Way, it might even trigger new rounds of starbirth, not just in itself, but in its neighbours. These kinds of chain reactions are becoming more interesting now that astronomers can observe examples of galaxy pairs elsewhere in the universe where star formation gets a clear kick from a close gravitational encounter. Tracking Triangulum's motion helps scientists put together a fuller picture, both of how our part of the universe works and of what will happen much further down the road. These predictions come with a good bit of uncertainty, and astronomers are always using new data to update their models. Still, with everything observed so far, there is a clear overall trend. Triangulum is on a path toward deeper involvement with Andromeda and the Milky Way, and the story is playing out across hundreds of millions and even billions of years. In addition to being a local example, Triangulum is a textbook case for understanding much broader cosmic structure. Most of the visible universe is made up of galaxies and galaxy groups joined together by gravity, and by studying the details of motion in cases like this, astronomers can test ideas about how the universe's biggest structures form and evolve. Because the local group is so close, its members are bright and detailed enough to allow high-precision measurements, unlike the murky, distant smudges of light for most other groups in our telescopes. If researchers can model the trajectory and interactions of Triangulum accurately, it makes their predictions about distant groups much stronger too. There are also interesting stories connected with certain features of the Triangulum galaxy itself that tie back to its larger motion. Some star clusters within Triangulum seem to have odd orbits or unusually high speeds compared to the rest of the galaxy. These could be the leftover signatures of past encounters, either with Andromeda, with smaller galaxies, or with clouds of intergalactic material along its journey. Occasionally, astronomers spot gas clouds or stellar streams that don't match the main rotation of the galaxy disk, which might point to debris torn loose during more tumultuous moments in its past. The approach of Triangulum is not only a gravitational affair, it is a process that people can actually watch unfold at a small annual scale, as new data pins down just how the speeds and positions are changing. Even amateur astronomers can participate in this, as better and better images taken years apart may show subtle changes that add up over a decade or more. For the most devoted skywatchers, this back and forth between new data and new predictions makes the galaxy feel just a bit more alive, as something that is truly moving and changing along with the universe around it. While it can be hard to grasp the timescales, the fact remains that the Triangulum galaxy is on a journey that links it directly to the fate of the Milky Way and Andromeda. Every burst of star formation, every faint ripple in the gas, and every shift of its spiral arms happens against the backdrop of a larger motion, a journey that stretches out over distances and time so large they reshape our sense of the universe itself. By tracking that motion, scientists are getting closer, bit by bit, to understanding what will come next for all of us here in this corner of the cosmos. Those detailed studies into Triangulum's movement set up a whole chain of events that astronomers have spent decades piecing together, bringing us face to face with the future destiny of these galaxies. When people talk about what's coming, they're usually referring to something that will happen over an unbelievably long timeline. Think billions of years. Yet scientists already have a fairly solid script for how things are likely to unfold, all thanks to precise measurements, careful math, and countless hours of observing. This big cosmic drama is not just a theory. It's based on genuine evidence and repeated observations that draw a picture of how the Milky Way, Triangulum, and Andromeda galaxies will eventually come together and reshape our corner of the universe in a way that's unlike anything we see today. The Milky Way and Andromeda, which is often called Messier 31, are on a direct course for each other, and their collision is the headline act, to use a casual phrase. Still, Triangulum, or Messier 33, is part of the same story and deserves more attention than it usually gets. Because Triangulum is smaller but still massive, its fate is interwoven tightly with these two giants. It seems that gravity will eventually pull all three galaxies into a monumental encounter that transforms the local group into a single supersized merged object, what astronomers describe as a supergalaxy. But this isn't a head-on crash like you'd see in a Hollywood movie. It's a lengthy, drawn-out event that will play out over several billion years. When astronomers model galactic mergers like this, they see that it all begins with the initial approach. Two galaxies draw closer, their mutual gravity gradually pulling them into a complicated dance. Long before the centers actually touch, their outer regions feel the first effects. As they get nearer, the gravitational pull gets stronger, and the stars, clouds of dust and gas start interacting in subtle and not so subtle ways. When Triangulum comes into this mix, it might first be captured in orbit around Andromeda or the newly merged Andromeda-Milky Way combination, passing by in sweeping arcs shaped by gravity. Over time, these orbits tighten, and each pass brings the galaxies closer together thanks to the way gravity dissipates energy and helps the systems shed momentum. Sometimes Triangulum might experience several close encounters, swinging around its more massive neighbours in elliptical orbits for millions of years at a time, each circuit slowly draining away a bit of its energy, especially as stars interact and gas clouds are compressed or even stripped away. During these passages, the gravitational forces do a lot more than just tug on the galaxies as a whole. They rip at the spiral arms and send shockwaves through the interstellar gas. That, in turn, can trigger massive episodes of new star formation, much more dramatic than what we see in any calm period. Some regions might suddenly light up with clusters of young blue stars, while other areas are stretched thin, their stars scattered into long, faint streams that wrap around the new merged structure. At the same time, some of the gas and dust gets pulled inward, funneled toward the new galactic center by the complicated interplay of all three galaxies' gravity. These flows feed bursts of activity at the center, including perhaps a flare-up around the supermassive black holes at the heart of each original galaxy, if they haven't already begun the slow process of spiraling together themselves. Gas that's not pulled into the center can get thrown out to the edges, sometimes even ejected entirely from the merged galaxy system, especially if strong starburst activity or black hole jets blaze in the core. Over hundreds of millions of years, the appearances of the original galaxies get more and more blurred, as their stars lose the patterns and motions that made them distinct spirals or disks. Instead, the sum of their parts starts to add up to something new. A single, much larger and more massive galaxy that may look nothing like the three original ones. In most models, what emerges is something closer to an elliptical galaxy, a huge, roughly football-shaped collection of stars and gas with very little regular structure compared to a spiral galaxy. The swirling arms and disks are pretty much gone at this point, having been twisted and mixed so thoroughly that no clear form remains. A supergalaxy like this could contain 1 trillion or more stars if you add up those from the original Milky Way, Andromeda, Triangulum, and any smaller galaxies that get swept up along the way. The new center of gravity is dominated by the results of all the black holes and dense star clusters funneling nearer and nearer together. Clusters of stars and enormous gas clouds may find themselves far from where they began, sometimes flung into loops that orbit through the outer edges, sometimes pulled into the glowing core. The timescales involved are much longer than anything you can imagine from everyday experience. Although Triangulum is flying toward its fate at roughly 100,000 kilometers per hour, the vast emptiness between galaxies means the whole event is stretched out over such a long period that to us, peering up at the sky, almost nothing noticeable would change for hundreds of thousands or even millions of years at a time. Calculations suggest that the main merger between Andromeda and the Milky Way will get underway 4 to 5 billion years from now, roughly when our own sun is reaching the end of its main life. Triangulum, being the smaller player, might come in a bit earlier or later, depending on the exact way gravity nudges its course, but once all three are caught up in mutual orbits, it's almost certain that they'll end up united over time. One detail often overlooked is that even when galaxies merge, practically none of the individual stars actually collide. Space inside a galaxy is so vast that the likelihood of two stars smashing into each other is almost non-existent. Instead, the gravitational pull rearranges where they go. Orbits get scrambled. Some stars, especially those originally in the outer arms, can get tossed far outward, perhaps even ejected into the wider reaches of intergalactic space as so-called rogue stars. Others get drawn inward to the new center, increasing the density and brightness there. The positions of solar systems shift, but the physical planets and suns themselves are totally unaffected by direct collisions. The merging process brings together not just stars, but the mysterious dark matter halos that surround all three galaxies. These halos are huge, invisible cocoons of mass that shape how galaxies behave. When the Milky Way, Andromeda, and Triangulum start to really interact, their dark matter halos will blend, shifting how gravity acts on everything inside and possibly helping the merged supergalaxy stabilize into its final form. All the smaller galaxies nearby, which are already part of the local group, could also be swept up in the process, making the ultimate supergalaxy even bigger. Some questions remain about the exact sequence. Will Triangulum merge with Andromeda before or after the main Milky Way-Andromeda collision? Simulations suggest either outcome is possible, with the odds depending on the tiny changes in movement and pull that add up over millions of years. Whichever comes first, Triangulum will either loop around Andromeda a few times, losing energy with each pass, or dive into the evolving system of the two galactic giants and merge not long after. There's also a chance Triangulum could be temporarily slung out in a wide arc, only to come back later as gravity slows it down and pulls it in again. These three-body problems, as scientists call them, are notoriously hard to solve perfectly, but the broad outlines are clear. These three galaxies are fated to combine. During all of this, the appearance of the sky as seen from Earth, or at least from wherever the solar system happens to be at the time, would change drastically, given a long enough timeline. Massive new star clouds might light up the sky as bursts of star formation are triggered by the mashed-up gas and dust. In the most intense phases, the core of the new supergalaxy could blaze with activity, shining far brighter than it does today, thanks to the concentrated energy of billions of new and dying stars, plus the feeding of black holes at the heart. Regions beyond the center would start to look altogether different as overlapping star fields grow thicker and whole swathes of space fill with stars and nebulae. While the merger process will strip away a lot of spiral structure, it will also leave behind traces of the original galaxies, massive stellar streams, huge population concentrations that once were cores or arms, and shells of stars flung outward from tidal interactions. Astronomers who study nearby examples of merged galaxies can often still pick out the fossil tracks of this kind of history, like faint echoes of the original participants, sometimes billions of years later. These types of encounters aren't unusual in the universe at large. Studies of distant galaxy clusters show us plenty of so-called red and dead elliptical galaxies that are the end result of repeated mergers, just like what's projected for the local group. In those systems, the main story is one of growth, collision, and transformation, driven over and over by gravity. What sets our region apart is that we have a close-up front-row seat for the process, even if the key events are still billions of years away. All through this grand transformation, the changing gravitational landscape could have other effects. Star clusters might be torn apart or spread out, some planetary systems might find their orbits changed slightly, and clouds of gas could be blasted out dozens or even hundreds of thousands of light years. Episodes of rapid star birth would inject new energy and light, while explosions of newly formed stellar giants would enrich the merged galaxy with fresh, heavy elements, altering the chemistry and the physical state of the new supergalaxy's interstellar medium. The centers of the original galaxies, each likely hiding a supermassive black hole, become the scene of some of the most dramatic evolution. When galaxies merge, those black holes can eventually spiral closer and closer, radiating gravitational waves, ripples in space-time, before finally merging themselves. This produces one spectacular event, releasing huge bursts of energy and possibly creating a single, even more massive black hole at the core. Such events would likely produce jets of energy and may shape the new supergalaxy's heart for millions of years afterward. Through this entire process, the merged supergalaxy grows more massive and pulls in even more material floating in the local group, including stars, gas clouds, and any small dwarf galaxies not yet gobbled up. In a sense, the boundaries of the new galaxy keep expanding as long as there's material within gravitational reach. Over time, this makes our newly created supergalaxy one of the true giants of the local universe. All this cosmic reshuffling has consequences for how planets and solar systems like ours move through this new environment. If the Sun and its family of planets survive these gravitational rearrangements without being ejected or broken up by tidal forces, their night sky will forever be changed. The familiar band of the Milky Way would vanish, replaced first by huge arcs and swirls of stars from Andromeda and Triangulum as they approach, then by dense new star fields after the mergers, and ultimately by a sky full of the mingled light of 1 trillion suns from the supergalaxy's mix. Every step of this process is driven by the unstoppable influence of gravity, guided by the initial conditions set way back when these galaxies formed. The outcome, one single colossal galaxy with new traits, a mixed-up history, and fresh bursts of star formation and black hole activity, is a natural endpoint for a galaxy group like ours. There's no need for anything spectacularly catastrophic to take place for the individual star systems. Instead, it's all about motion, slow changes, and the grand reorganization of billions of stars. Right now, astronomers keep a close eye not just on the headline acts, the Milky Way and Andromeda, but on Triangulum, because the timing, speed, and nature of its encounter with the other two will tweak exactly how the final supergalaxy turns out. Will it add fuel for more starburst activity? Will its approach shake loose more dwarf galaxies, or bring in streams of gas that power new stars? The questions are big, but the methods for answering them are improving every year. Observatories both on the ground and in space keep refining the map of our region, tracking motions, measuring speeds, and spotting faint structural features that will eventually provide the full story. So the destiny locked into this three-galaxy system is neither sudden nor destructive at the level of stars and worlds. Instead, it's an evolutionary story of orbits winding down, patterns dissolving, and new forms being created from what came before. After billions of years, well past anything our species will likely witness, the Milky Way, Andromeda, Triangulum, and their smaller companions will become something wholly new. One vast supergalaxy, reshaped by all those epic encounters, mixing chemicals from billions of stars, and offering a new foundation for whatever cosmic events play out in this corner of the universe next. All this talk of galaxies merging over the course of billions of years naturally leads to a pretty common question. What is actually taking place while these massive structures draw together and form one enormous new galaxy? There's this image a lot of people have in their heads, maybe something from a movie or a documentary, of galaxies smashing together, stars crashing into one another, and everything getting torn apart like a cosmic disaster. But when astronomers get into the specifics of how galactic collisions really work, things turn out to be a whole lot more complex, and in many ways, more interesting than that. The reality, as revealed by observations and computer models, shows that while the overall scene is dramatic, the details are packed with subtlety, cause and effect, and an ongoing reshaping of not just the appearance of galaxies, but also how stars, gas, and even black holes behave inside them. Let's go straight to the basics about stars during a merger, because that's where many people worry about cataclysmic impacts. You might imagine a situation where each of the billions of stars in one galaxy are on a certain path. Then when another galaxy plunges through, stars start colliding, maybe even destroying each other, but that's not what happens at all. Even though each galaxy can contain hundreds of billions of stars, the space inside a galaxy is mind-blowingly vast. On average, stars are separated by several light years, and even in the middle of a busy spiral galaxy, the chances of two stars hitting one another directly are, for all practical purposes, zero. There will be some gravitational nudges, yes. Stars can get their orbits altered or be tossed onto new paths entirely, but collisions are almost non-existent. Instead, as the merger unfolds, the population of stars gets mixed up, scrambled, and tossed around into new distributions, but individual stars just keep orbiting the center of mass, however much it might shift. A really big part of the action during a collision comes down to gas and dust. These aren't neatly packed objects, but sprawling clouds and clumps that make up a significant chunk of what makes a galactic disk appear bright and lively. When galaxies come together, their interstellar gas doesn't politely ignore its neighbor. Instead, clouds crash together, shock waves ripple through, and gravity compresses gas into new zones. These collisions make the gas slow down and pile up, and when that happens, it gets squeezed so tightly that new rounds of star formation kick off all at once. In fact, some of the most spectacular starburst regions observed in the known universe are happening inside galaxies caught in mergers. In those places, the pace of starbirth can skyrocket. Sometimes astronomers see hundreds of new stars form in just a single year, compared to just a handful in a tranquil galaxy. Every time this kind of burst occurs, the new massive stars shine hot and blue and they burn out quickly. Then, over just a few million years, they go supernova, spreading heavy elements into their surroundings and making the interstellar medium even richer for the next generation of stars. Some of this material ends up in new planets, some is thrown off into intergalactic space, and some fuels ongoing star formation, so the story is constantly cycling. With the Milky Way, Andromeda, and Triangulum expected to merge, astronomers predict many fresh waves of these starbursts as the gas in all three galaxies gets tossed together, compressed, and shocked. Apart from gas and stars, another part of the story is what happens to the overall shapes of galaxies. Spirals and the beautiful arms that define them are very sensitive to gravitational tugs. In the early stages of a merger, the outer edges are the first to react. Whole swathes of stars get pulled out into long, thin streams that arc around the main bodies of the merging galaxies. These are called tidal tails, and they can stretch for hundreds of thousands of light years. Over time, as the galaxies continue to interact, their distinct disks blur together. The neat spiral arms fade as stars and gas are thrown into new orbits, settling down into a more featureless, football-shaped cloud. From start to finish, these visible changes can take hundreds of millions of years to really come together, but the evidence for these processes is right in front of our telescopes. Astronomers spot tidal tails, shells, and warped disks in other galaxies all the time, and these features are fossil records of previous galactic encounters. One more piece of the puzzle lies at the very core of the merging galaxies. The supermassive black holes found at the center of almost all large galaxies, including the Milky Way and Andromeda, and probably Triangulum as well. During the long merger process, as galaxies pass closer and closer, their central black holes begin to move together as well. At first, they swing around the combined system, gradually losing energy as they interact with the surrounding stars and clouds. Eventually, if the orbits shrink enough, the black holes themselves can merge, combining into a new, larger black hole at the core of the supergalaxy. The merging of black holes is one of the most energetic and fascinating events that can happen in the universe. When this happens, huge gravitational waves ripple out, and astronomers believe that one day these events will be detected even across billions of light years. Galaxies merging is not just a reshuffling of the visible stuff, stars, gas, dust, black holes, but also of the unseen dark matter halos that wrap around and through all of them. This dark matter might not give off light or interact with other matter in any way we can see, but its gravity acts across every stage of the merger. The final shape, rotation, and stability of the merged galaxy depend greatly on how all this hidden mass pulls on the stars and gas. This is what holds the whole supergalaxy together at the end, and also sets the stage for how fast it spins, how flat or round it appears, and even where future dwarf galaxies and satellites will settle in the new order. Another fascinating process in a merger is what scientists call violent relaxation. That just means as the gravity of the combined galaxies mixes everything up, the stars settle from their original neat orbits into new patterns. These can be more random and less organized than what existed before. As a result, the merged galaxy often switches from having clear disc-shaped structure to looking more like an ellipse or a great sphere. Most of the old spiral features, with their flat rotation and thin structure, disappear through this process, replaced by the kind of dense scattering of stars seen in big elliptical galaxies. While all this is going on inside the merging galaxies, there are even more subtle effects happening out in the outskirts and to smaller objects nearby. The shifting gravitational landscape during a merger can disrupt or even break apart some of the lesser star clusters and dwarf galaxies. Satellites orbiting around, pulled this way and that, can either spiral inwards to join the new supergalaxy or get flung out on new orbits, sometimes leaving the merged system entirely. This is one way scientists think some lone wandering galaxies may have started their journeys across the cosmos. During these vast timescales, there are plenty of star systems that can get shifted from their previous locations. Some stars, especially those on the outskirts, can pick up enough speed during the merger that gravity flings them out beyond the reach of the main galaxy. These are sometimes called intergalactic stars or rogue stars. While there is little impact on the star itself, it now travels alone, slowly orbiting the central mass, or even leaving the local group altogether if kicked hard enough. Interestingly, this could happen to whole clusters of stars, not just individuals, giving us even more clues about how galaxies interact by spotting these faint, far-flung castaways. There's another interesting layer to all this. Star clusters and massive clouds of gas and dust can sometimes survive the merger relatively intact if they're dense or lucky enough to avoid the more chaotic regions. These clusters can then become part of the new supergalaxy's halo, orbiting far outside the visible core. Over many more billions of years, some might get drawn in toward the center, or keep looping around on long, slow orbits, gradually dispersing as the stars go their separate ways. For gas clouds, not all of them end up fueling new star formation. Some get blasted out by intense starbursts or by jets and winds coming from the activity near the new black hole at the center. Once forced outside, these clouds might form faint new streams of their own, or fade away into the dim background of intergalactic space. Others may eventually rain back down onto the galaxy, providing new fuel for star formation far after the main merger is over. Looking at actual cases elsewhere in the universe, astronomers have observed all stages of these collisions. In some merging systems, there are bright arcs of new stars, glowing regions lit up by recent bursts of activity, wild tails of scattered stars looping outside the main disks, and central areas that shine almost blindingly because of so much gas and star formation jammed into one spot. Some of these galaxies show evidence that star formation can be both triggered and quenched during a merger. Regions light up as new stars form, but then energy from exploding supernovae and feeding black holes can heat up gas enough that it cannot collapse anymore, shutting down star formation in some parts. Computer simulations help to fill gaps in what we can't see directly by allowing scientists to change the numbers, like changing the angle of approach, the amount of gas, or the speed of the galaxies, and see how every one of those factors changes the story. For example, a merger between two gas-rich spirals can make a huge, bright elliptical galaxy, but if one galaxy is dry, meaning it has little gas left, the final shape can be very different and possibly less active in terms of new stars being born. The details of these models also test out ideas about dark matter, gravity, and how galaxies fit together inside cosmic structures, making each new run of the computer a small window into the future or the past of the universe. If you try to imagine a timeline, the first close pass of the galaxies often doesn't lead straight to a merger. It sets up a series of swings, close encounters separated by maybe hundreds of millions of years, where the galaxies overlap gravitationally, pull stars and gas out in great arcs, then swing past each other, winding back until friction and continued interactions finally settle the whole bunch into one object. Each encounter strips away some ordered motion, bringing parts of one or both galaxies into the growing, mixed-up mass. It could take several passes before the original galaxies fully lose their separate identities and settle into a single new structure. An even deeper outcome of all this reshuffling is that the chemical makeup of the new galaxy gets more complex too. Every round of star formation creates new heavy elements, things like iron, silicon, carbon, and more. These elements build up over generations of stars, so when you blend three galaxies, each with their own star-making histories, you end up with a supergalaxy sprinkled with more elements necessary for planet building, new generations of stars, and perhaps the variety you'd need if life is ever to take hold anywhere else. After all these wild changes, the end result is typically one massive, featureless galaxy, with a centralized bulge and a halo of old stars and smaller galaxies that were left over or pulled in during the violence. That single supergalaxy, likely elliptical, slowly calms down. New star formation eventually tapers off as the last gas is either used up or blown away, leaving a huge realm of older stars shining on, merging their collected histories in a steady, quiet glow for billions of years to come. For astronomers, what's so useful about watching or simulating these collisions is that it tells us how common and important galaxy mergers are in shaping the universe. A lot of the big elliptical galaxies we see now are the byproducts of earlier collisions, and the way their stars are scattered, or the faint traces of disrupted arms and tidal tails, offer a kind of fossil record. Matching patterns in these galaxies to our own projections for the local group helps check and refine the models. Returning to black holes for a second, it's not only the final merger that matters. As the central black holes spiral in toward one another over millions of years, they can form binary orbits, swinging around each other, stirring up gas and stars in the very center. These binaries are of huge interest in astrophysics, especially now that we're just starting to detect gravitational waves from these mergers using special observatories. When the final coalescence happens, the burst of gravitational waves is an echo through space-time, signaling a history of violence and renewal. Mergers also help in understanding how galaxy groups and clusters work at even bigger scales. When several medium-sized galaxies blend, they set the tone for how their whole cluster will look in billions of years. The interactions during each merger help dictate how stars and dark matter get spread out, how quickly subsequent mergers can happen, and even how the overall population of galaxies in a region will evolve over time. Through all these vast processes, it's important to remember the slow pace on human timescales. These changes look dramatic in simulations that speed up the action, but in reality, even the fireworks of a galaxy merger are stretched out across hundreds of millions or billions of years. If you could somehow stand outside the system and watch the whole thing unfold in real time, you'd see one group of stars drawn in here, a cloud of gas set alight over there, one galaxy's disk warped and torn, and over ages, the slow blending into something much bigger and entirely new. This is how nature builds the great structures of the cosmos, by observing, simulating, and exploring mergers from every possible perspective, whether it's looking for tidal tails, freshly sparked starbursts, or the subtle echoes of black hole collisions. Scientists keep working to pull every last bit of information from these dramatic but slow events. There's always more to learn about the mechanics of merging galaxies and the aftershocks those processes send rippling through the universe, shaping what we see today on the grandest scales. When astronomers break down the full chain reaction of what happens in planetary systems as galaxies come together, it gets personal for a lot of people. All this talk about galaxies swirling, merging, and forming supergalaxies eventually brings the question right to our backyard. What, if anything, actually happens to Earth and the rest of the solar system as the Milky Way, Andromeda, and Triangulum come together? Since these galactic events unfold over billions of years and involve unimaginable distances, it's not always obvious how the solar system gets shuffled around, or whether anything truly threatening ever comes our way. But the story is a lot more specific than just nothing happens, or everything gets destroyed. The answer comes down to the details of motion, timing, gravity, and the sheer size of these systems. The solar system is currently sitting a bit more than 25,000 light-years from the center of the Milky Way. That puts us well inside the galaxy's disk, but still enough distance from the crowded core to avoid most of the coolest and most dangerous cosmic events, at least for now. As the Milky Way and Andromeda draw closer over the next 4 to 5 billion years, and as Triangulum potentially joins the mix, the first changes that matter for us will still not be anything anyone would notice in a single human lifetime. The mergers kick in so slowly that it takes hundreds of millions of years just for one galaxy to start looking different as seen from any planet inside it. If you zoomed out, you'd see the Milky Way's shape start to warp as tidal forces from Andromeda's massive pull begin tugging on the outer arms, and slowly the pattern of stars in our sky starts to change. Long before the actual merger, Andromeda will become more and more prominent in the Earth's night sky. Today, you can just barely see it as a faint blur if you know exactly where to look on a clear, dark night. But in about 2 billion years, it will look brighter and larger as it approaches. Over the next few billion years, as the gap between the galaxies closes, the appearance of Andromeda will gradually dominate the sky, growing to rival, then surpass, the Milky Way's own core in brightness and size. Triangulum, being smaller but still massive, may also be visible as a dramatic object, especially if it swings close by before getting swept up in the larger merger. The most important question for the solar system's future during all this is, does the Sun and its orbit stay stable or get thrown into a completely new trajectory? Even though the galaxies are colliding and their overall shapes are getting dramatically changed, most actual stars, including the Sun, are likely to avoid close encounters with other stars. There are just too few stars relative to the gigantic expanse of space. When galaxies pass through one another, the main effect isn't stars smashing together, but gravity rewriting the orbits of everything inside the galaxies. The collective pull from all the matter, stars, dark matter, gas, and more, determines where everything ends up. Computer models of these mergers show that there are a few possible paths for the solar system when everything finally comes together. One possibility is that the Sun, along with Earth and the rest of the planets, simply migrates along with a huge chunk of the Milky Way's disk, blending right into the new supergalaxy's overall structure. In this case, the Sun's orbit around whatever remains as the center of the new galaxy could end up looking pretty similar for a while, though over time, the combined gravity of billions of other stars and clouds of dark matter might gradually nudge the solar system's path into something new. Our system might move in closer to the newly formed elliptical core, or it could get bumped farther out, swirling among the thick halo of stars that forms as everything settles down. A second scenario, a bit rarer but definitely possible, is that the Sun ends up in a dramatically shifted orbit as a result of all the gravitational chaos. If the solar system was unlucky enough to pass too close to a massive region where stars and gas were getting tossed about, its path around the galactic center might get kicked into a much wider orbit, or even shot out to the outer reaches of the supergalaxy's envelope. There's even a small chance, supported by some simulations, that the Sun could be ejected from the newly merged galaxy entirely, launched into the vast emptiness between galaxies as a so-called rogue star. In this unlikely case, the planets would still keep orbiting the Sun as usual, but everything outside the solar system, the wider cosmic backdrop, would look totally different. Instead of drifting in the middle of a galaxy, the night sky would be much darker, with only the faint glow of the merged galaxy and other far-off galaxies to see. Yet another possibility, and probably the most statistically likely, is that the solar system stays within the general neighbourhood it started in, but with some nudges to its orbit and a serious remix of the night sky. Over many millions of years, the solar system's location would drift in relation to the chaos of the merging process. But unless some huge gravitational event sends it spinning away, Earth and its planets would simply become part of the supergalaxy's background noise, orbiting the new centre in what would eventually settle into a steady path. Though maybe not the tidy, stable circle around the Milky Way centre we follow now. What about the physical effect on Earth and life itself? The stunning truth is that none of these scenarios are likely to drastically affect the actual orbit of Earth around the Sun, the gravitational forces holding the solar system together, or the day-to-day conditions on our planet. The distances between stars, even during a merger, are just so enormous that while stars reposition themselves, solar systems themselves aren't broken up. Over the lifetime of the Milky Way, very few stars have been close enough to us to seriously disrupt the outer solar system, and during a merger, those odds change only a tiny bit. Direct hits are almost impossible. For humans or any other life on Earth, the main cosmic story is basically a constantly evolving panorama in the night sky, not a sudden disaster or a burst of intense energy that could harm life. There are a few indirect effects that could be worth thinking about, even though they are far more subtle and slow. One is the possible migration of heavily irradiated gas clouds or star-forming regions. During galactic mergers, some regions get sudden boosts in star formation, and some supernova explosions occur as a result of very massive stars dying young. A nearby supernova, close enough to Earth to actually impact our atmosphere or biosphere, is still extremely unlikely to happen as a direct result of the merger, simply due to the sheer scale of the universe. But statistically, the overall rate of close supernova could rise just a little, and over millions of years that might affect the cosmic ray environment slightly. Even then, for life on Earth, the most serious changes still would come from processes inside our own solar system, such as the evolving brightness of the Sun, volcanic activity, or asteroid impacts. Meanwhile, the skies would become far more beautiful and unpredictable. As whole new galaxies approach and eventually mix with ours, the number and brightness of stars above would increase. Instead of the Milky Way's hazy band across the sky, entire new arcs and patches would be visible. During the time when Andromeda and then Triangulum are closing in, both galaxies might be visible as enormous swaths, taking up much of the sky. Once the galaxies actually merge, the distribution of stars wouldn't be a neat flat band anymore, but instead a swirl or ball of stars, glowing with a diffuse and ever-changing arrangement. Some especially dense star clusters might glow like never before, and nebulae from ongoing starbirth could light up like cosmic beacons. Now consider the fate of the solar system if it happens to get kicked into intergalactic space as a result of these gravitational interactions. This is a low probability, but not zero. In simulations where the Milky Way merges with one or two other galaxies, a small percentage, maybe a fraction of a percent, of Sun-like stars are given enough gravitational energy to leave their host altogether. If that were to happen to the Sun, the solar system would no longer be part of any galaxy. The planets would still orbit just as they always have, held close by the Sun's gravity. The night sky, though, would never look the same. All those familiar star fields would be replaced by a relatively blank backdrop with only a faint smudge of stars, what's left of the merged galaxy. visible in the far distance. Earth's seasons, tides, and basic environment wouldn't be affected by this ejection, but the constellations and star patterns in the night sky would be unrecognizable. Another factor that comes into play is the fate of the Oort cloud and other distant icy objects that orbit the Sun far beyond Pluto. The outer regions of the solar system are more weakly bound to the Sun, so a close gravitational encounter during the chaos of the merger could strip off some of these comets, or even stir up a burst of cometary activity. This could increase the chance of comet impacts in the inner solar system over long timescales, but for that to happen, a precise set of circumstances would need to line up, far more rare than most doom and gloom scenarios you might hear. Even then, this kind of thing is already possible during close passages of other stars and hasn't been a major factor over the history of Earth's habitability. Across all likely scenarios, direct impacts on Earth and the planets themselves from the merging process are vanishingly rare. There are no mechanisms specific to galactic mergers that would render Earth uninhabitable simply due to shifts in position or new star fields lighting up. The variables that matter most to the fate of life here are still local ones: changes in the Sun's energy output, asteroid and comet strikes, plate tectonics, and the evolution of the atmosphere. One interesting wrinkle comes from the very long time scale of this whole process. By the time the Milky Way, Andromeda, and Triangulum have finished combining into one new galaxy, something like 5 or 6 billion years from now, the Sun will be nearing the end of its own life as a main sequence star. Scientists expect that, around this time, the Sun will become a red giant, expanding and possibly engulfing Mercury, Venus, and maybe even Earth itself. Even if Earth escapes, the surface conditions will become unlivable, the oceans evaporate, and any surviving life would have to be extremely tough or hidden well below ground. In other words, the fate of Earth and its place in the universe is tied just as much to the life cycle of the Sun as it is to the fate of the galaxy. If humanity, or our descendants, ever become a spacefaring species, the future galactic changes could open up new opportunities over unimaginably long timescales. New star fields and nebulae could make for incredible sights. Maybe even someday civilizations might catalogue the mergers happening and trace their star's place in the grander flow of galactic material. But as for Earth itself, besides the far-flung possibility of getting kicked out as a rogue system, the main effect of the Triangulum and Andromeda mergers is a rearrangement of the cosmic scenery. Another area where astronomers pay extra attention is the effect on nearby planetary systems, especially those rich in gas and dust. Mergers can compress gas clouds, leading to new rounds of star formation. Some models suggest that new, massive stars formed during these bursts could produce harmful radiation or send shockwaves through space, but the vast distances involved still mean the solar system is likely to be protected from most direct harm. Local star clusters might become more densely packed, but unless a neighbouring star swings very close to the solar system, which is unlikely, the solar system's own stability isn't threatened. Lastly, while all this is going on over billions of years, the solar system will also continue its slow drift through the larger halo of the supergalaxy to be. Over that time, the Sun's motion and that of its siblings, the other stars born in the same cluster, will become increasingly randomized as gravity shuffles stars from the Milky Way, Andromeda, and Triangulum together. Some may pass nearer than before, changing the overall look of the night sky, but the gravitational bonds that keep the Sun and planets together remain so strong that only the most unlikely close pass could alter life in any serious way. So to sum it up, the coming together of the Milky Way, Andromeda, and Triangulum is a majestic cosmic event with effects that play out over such long timescales that to any creatures living on Earth, it's mostly a matter of amazing changes in the night sky. The solar system and the planets within it continue on their paths, with the biggest threats to life coming not from the galactic merger, but from the long-term changes inside the Sun and on Earth's own surface. Whether we stay part of the new galactic giant, get flung farther out, or, on that extremely rare chance, ejected into intergalactic space, our survival is much less about the fate of the galaxies and much more about keeping our own cosmic house in order. As these grand mergers play out, the universe above us will keep shifting, lighting up new constellations and patterns, and putting on a show for whoever might still be around billions of years from now to see it. The shifting positions of the Milky Way, Andromeda, and Triangulum galaxies are going to rewrite the map of our night sky in ways that are almost impossible to overstate. While the fate of Earth and the solar system during these mergers is mostly a story about safe orbits and long, steady cosmic journeys, the sky overhead is where we'll see the most spectacular transformation, at least for anyone or anything still watching from the surface of our planet in a few billion years. What we know right now is just a hint of what's to come, based on computer models, careful telescope observation, and the work of astronomers who study how galaxies blend and change over time. If we look up on a clear, moonless night today, the Milky Way appears as a faint band of cloudy light made up of countless distant stars jammed so tightly together that our eyes can barely pick them apart. The Andromeda Galaxy, if you happen to be in a rural area with no light pollution, is just barely visible as a smudge, easy to miss if you don't know exactly where to scan the sky. Triangulum is even fainter, something most people who don't use binoculars or a telescope will never notice. But over the next few billion years, all three of these galaxies aren't just going to stay where they are. The slow-motion gravitational approach will make these distant neighbours loom ever larger and brighter. According to calculations tracking the future movement of these galaxies, Andromeda will be the first to announce its arrival. Right now, it's about 2.5 million light-years away, but it's headed toward us at a speed of about 110 kilometers per second. As hundreds of millions of years pass, the galaxy will grow brighter and bigger in the sky, moving from a faint blur to a spectacular glowing spiral, quite unlike anything we see today. The change will be slow, a little more luminous each 1,000 years, a bit more spread out across the sky every 10,000 years, but get far enough ahead in this timeline, maybe 2 billion years in the future, and Andromeda will be the most dazzling single object anyone would ever see at night. It will stretch wider than the full moon, with details visible to the naked eye that today require the largest backyard telescopes. Triangulum, the smaller and dimmer companion, will go through a similar transformation, although on a slightly different schedule. Its direction of approach and its speed relative to the Milky Way mean that, depending on the fine details of their orbits, Triangulum may be pulled closer to Andromeda in a kind of orbital dance, or it might swing closer to us along another arc. Either way, as Triangulum joins the gravitational action, it too will bloom into view, no longer hiding in the darkness but putting on a show as a ghostly spiral or spreading patch of light. As these galaxies close in, the first obvious result for stargazers will be that familiar constellations, Orion, Cassiopeia, Ursa Major, start to get crowded out. Instead of the current pattern of stars, new arcs, knots and streaks of distant suns and nebulae will flood the sky. Any society living through these epochs would have to redraw every map of the heavens and invent new names for these spectacular features. Old constellations would fade, covered up or replaced by thousands upon thousands of new, bright points of light that gradually outshine the patterns we've known. Just before full-on galactic merger, the sky will probably be at its most jaw-dropping. Andromeda, by that point, could easily be so large and luminous that it dominates a massive swath of the sky, from one horizon to the other, possibly 10 times the width of the full moon. The spiral arms, scattered clusters, and star-forming regions would become apparent even to the naked eye. You'd see entire glowing clouds of gas, bright blue clumps of new stars, and bands of dust slicing across the whole display. If you could line up Andromeda and the Milky Way's core, the visual effect would rival or even overwhelm the combined light of all other stars in our galaxy. Triangulum may not match Andromeda in pure size, but it brings its own sights. When it swings closest to the Milky Way, it could appear as an elongated or distorted patch, its shape pulled and stretched by the competing gravity of its bigger cousins. Its star clusters, regions of bright pink nebulae, and its loose spiral arms could show up in the sky as subtle details, perhaps blurring into Andromeda's features or standing out as their own arc. Now, once the full merger process starts, over periods of several 100 million years, the beauty and drama reach a whole new level. This is the era of maximal cosmic fireworks. As the galaxies interact, long streams of stars are ripped away and cast into space, visible from Earth as slow-moving arcs and bridges of starlight. These are the famous tidal tails that astronomers see in colliding galaxies elsewhere in the universe. Nebulae, already bright from star formation, get even more intense as clouds of gas are crunched together. The result? Starburst regions glowing in blue and purple, sprawling immense ribbons of radiance from horizon to horizon. The night sky, over generations, would lose the crisp line of the Milky Way but gain enormous diffuse whirls and cloudy structures, shifting over millennia as the merger plays out. It would be unlike anything seen on Earth before. Each century, small changes compiled across millions of years would grow into new structures and displays. And as Andromeda's and Triangulum's most distant stars mix with the Milky Way's, the total number of visible stars from our point of view could increase dramatically, possibly from just a few thousand visible to the naked eye on a moonless night, up to tens or even hundreds of thousands. One thing to keep in mind is that these changes don't happen all at once. The timeline is measured in millions and billions of years. Our current constellations won't simply vanish. They'll slowly drift, stretch, and eventually be overtaken by these new bands of stars and nebulae. If you snapped photos every 10,000 years, you'd see the difference. But on a human scale, it's like the hands of a cosmic clock creeping along almost imperceptibly. Yet, for any civilization that survives over such lengths of time and keeps records, the changing sky would be undeniable. It's not just the sheer number of new stars that would appear, either. It's the overall colour, brightness, and arrangement of light in the sky. As the galaxy merger triggers waves of new star formation, entire regions light up with young blue stars that outshine the average stars we see today. The centres of the merging galaxies, where black holes might be feeding, gas clouds collapsing, and star clusters exploding into existence, could become so bright they'd be visible even through layers of gas and dust. Some distant night, the sky might never be completely dark again at certain times of year, thanks to these persistent bands and clumps of starlight. As time moves past the chaos of merger and the new supergalaxy takes shape, the bright arcs and tidal tails settle down. The end result, after a few billion years, will probably be a sky dominated by a huge elliptical glow, more like the blurry patch of a giant galaxy than the crisp, banded disk we see now. There would still be star fields and clusters, but their patterns would be different, their spread much broader, and the new night sky would never return to what we call familiar. Constellations old and new would be rearranged again, and Earth would orbit within a realm surrounded by trillions of mingled stars from what used to be 3 separate galaxies. Taking a step back, astronomers look to other galaxies for clues on just how complex and beautiful these changes might be. When we observe collisions between galaxies elsewhere in the cosmos, the most striking features are always the elaborate bridges and tails of stars, the glowing starburst clouds, and the central bulges that burn with the activity of merged black holes and swirling gas. Our own future sky will mimic these sights, only even more vivid because of our unique perspective from the inside. What's especially wild is imagining how all this would look from different places in the solar system. If you were on Mars, Titan, or even Pluto, the merging galaxies would display the same cosmic ballet, but with possibly sharper detail thanks to thin or almost non-existent atmospheres. If humans or any other life make it out to deep space, the changing galaxy would frame every future journey, every sunrise, every new home among the stars. There's another detail to think about. As galaxies merge, some stars and whole clusters might get thrown far from their homes, meaning that strange new fast-moving stars could suddenly light up the sky, or fade forever as they leave the neighborhood. Earth's own view of the galaxy could change if our sun gets nudged to a new location in the supergalaxy, or even pitched out entirely, though that's rare. In those cases, the new night sky would reflect not only the merger, but also the sun's new journey through space. Long before Andromeda reaches us, the changing night sky itself will serve as advance warning. The first hints will be the brightening and widening of the galaxy's disk on the horizon. For generations, stargazers will watch it grow, cataloguing each new clump of light and giving names to new nebulae and fields. Society, if it's still awake and curious, will need new maps, new legends, and a renewed sense of the universe's size. Through it all, there will be no single night when things suddenly look different. The transformation will come through steady, almost invisible change. Yet, for future astronomers, maybe thousands, millions, or billions of years from now, this evolving sky will be the greatest demonstration yet that the universe is always in motion, always changing, and always offering new wonders to anyone patient enough to look up. All of this shows just how much the story of our galaxy's future is written above us. While galaxies merge and settle, the heavens will glow with new stars, arcs and clouds, and the view from Earth will become a living record of cosmic evolution, unfolding not just for scientists, but for anyone who takes a moment to step out on a clear night and gaze up at the stars. When you think about how much the night sky is bound to change as the Milky Way, Andromeda and Triangulum galaxies start drifting together, it becomes pretty clear how crucial it is to study other places where this sort of thing is happening right now. Luckily, the universe isn't shy on examples. It's packed with other galaxies caught in the act of merging or colliding, playing out in real time everywhere from our own neighborhood to the farthest reaches astronomers can glimpse. Every time scientists look at one of these cosmic mashups, they get a clearer idea of what lies ahead for us, and those observations help paint a better picture of how galaxy groups like ours actually evolve and what sort of surprises might come along. Take the Antennae galaxies, for example. These are two spiral galaxies tangled together about 70 million light-years away in the constellation Corvus. If you point a big enough telescope at them, you can see their arms stretching out like the antennae on an insect, hence the name. What's happening there is a full-on, slow-motion collision. Both galaxies are pulling and twisting each other, flinging out massive bridges of stars and clouds of gas that stretch tens of thousands of light-years. In those tidal tails, astronomers have spotted giant clusters of young blue stars, proof that these wild gravitational events actually trigger fresh waves of star formation. By studying how these stars light up and how the gas is moving, researchers get direct insight into what will likely happen when the Milky Way and its neighbours go through the same process. Then there's the Whirlpool Galaxy, or M51. It's around 30 million light-years from us, and what makes it special is it's currently interacting with a smaller companion galaxy. This pairing has created visible shockwaves in the spiral arms of the main galaxy, compressing clouds of gas and kicking starbirth into high gear in some areas. High-resolution images reveal dust lanes, bright knots of newly formed stars, and complex twists in the structure. Real, tangible evidence of what happens when galaxies don't just pass by each other, but actually start grabbing and pulling on every bit of material they contain. Observing other galactic mergers goes way beyond just snapping pretty pictures. Astronomers use every tool at their disposal: optical telescopes, radio observatories, X-ray satellites, and more recently, gravitational wave detectors to break down what's happening across the spectrum. Looking in different types of light reveals different parts of the puzzle. For example, X-rays can show regions where intergalactic gas is getting superheated, sometimes by the crashing together of clouds or the furious winds from newly formed massive stars and their supernovas. Radio telescopes are great at picking out cold gas that's getting compressed or stripped away. By piecing together results from each wavelength, researchers figure out how fast galaxies lose or gain gas, how stars are born during mergers, and how the shapes of whole galaxies get rearranged. One thing astronomers have learned from looking at these examples is that even when the big picture looks violent, two or more galaxies blending into one, most stars and planets inside remain remarkably untouched. The chance that two stars will strike each other directly is almost nil, just as the numbers predict for our own merger scenario. The space between stars is so vast that even in a mess of spirals swirling together, most stars stay on their own paths. What does shift, however, is the complex ballet of all those orbits. These changes can sling some stars to new orbits, sometimes far from their original home, occasionally enough that they become rogue stars wandering between galaxies, just like what might someday happen to stars from the Milky Way or Triangulum. Looking at merging systems like the Antennae and the Whirlpool, it's also super clear that these events are usually the main drivers behind huge batches of new star formation. As clouds of gas smash together or get compressed by moving shockwaves, they collapse and new stars pop up in tight clusters. Sometimes these even outshine their parent galaxies for a while. In the early universe, mergers were probably the main way massive galaxies grew so quickly, gobbling up smaller ones and constantly refreshing their supply of gas for new stars. When scientists look at snapshots across billions of years, they see that galaxy growth is often anything but gentle. Collisions, near misses, and ongoing mergers are written all over the history of the cosmos. Another critical discovery that comes from watching other galaxy collisions is how certain features stick around, even long after a merger is finished. For example, some merged galaxies still have visible tidal tails or loops, long arcs of stars pulled out by gravity and never quite recaptured. Others have dense star clusters that were formed during the chaos and now orbit as relics of the collision. You can also find regions in the centers of some merged galaxies that are still boiling with star formation millions of years after the rest of the galaxy has quieted down. Astronomers have found these echoes in systems as far as 1 billion light-years away for theoretical models and computer simulations. These observations from real galaxies act as a truth check. Researchers use data from places like the Antennae and the Tadpole Galaxy, the latter famous for its sweeping tail of stars after a recent merger, to hone their predictions for our own local group. By watching how quickly gas gets used up, or how star clusters survive, or how long tidal tails last, they can fine-tune exactly how they expect the Milky Way and its companions to blend together. If a simulation says something should last for 100 million years but it hangs on in real galaxies for twice as long, the model gets updated accordingly. And these mergers aren't just about changing the design of a galaxy, they're fundamental for understanding the chemistry and evolution of the universe as a whole. In almost every case, these galactic pileups lead to an increase in heavy element production. Supernova explosions scatter elements like oxygen, carbon, iron, and more. Everything needed for rocky planets and maybe for building blocks of life. It's during wild episodes of galactic overlap that much of this mixing and enrichment seems to happen. Astronomers often find that galaxies with the most active mergers in their past have disks, halos, and star clusters with far more heavy elements than their quieter cousins. Observing merging galaxies also helps scientists understand what happens at the very center where the biggest changes occur. Most large galaxies, including the Milky Way and Andromeda, are believed to have supermassive black holes in their cores. When galaxies combine, their black holes can spiral together over time, eventually merging into one supermassive object. This process releases powerful gravitational waves, actual ripples in space-time, that can now be picked up, at least in principle, by detectors here on Earth. By looking at galactic centers where black holes might have already fused, or are on the way to doing so, scientists get rare glimpses into how these monster black holes grow, influence their environment, and sometimes shoot out jets of material that can stretch for thousands of light years. Some favorite laboratory galaxies among astronomers are the ultra-luminous infrared galaxies ULIRGS. These are usually the result of huge mergers where so much dust and gas gets compressed that the galaxies outshine everything around them in infrared light. The heat from rapid star formation and feeding black holes is so intense that it can be detected even when the distant galaxy's own stars are hidden by dust. This is exactly the kind of scene that might play out in the early 100 million years after the Milky Way, Andromeda, and Triangulum start merging, starbursts, dust clouds, and maybe even short-lived hidden galaxy phases. In addition, observing nearby mergers is a way to practice and refine all the tools and software that astronomers will need to study the local group's future. If you know what to look for in the chaos of a far-off collision, you're better equipped to predict exactly how stars, clusters, and whole solar systems move and change during the much slower drama at home. It's this kind of practice that makes it possible to predict the fate of the sun and planets, or figure out how the light show in Earth's sky will change as 3 major galaxies blend. The lesson from all this is that while galaxy mergers are spectacular and unique events, they often leave the individual contents mostly intact, just redistributed, compressed, or spread throughout the new supergalaxy. And in almost every case, the aftermath of merging is a more massive galaxy with lots of age differences between its stars, enriched with new elements and packed with star clusters. You can also spot differences in how tightly packed the stars are and how much star-forming gas remains in different regions. By studying galaxies at every merger stage, from the first signs of tidal stretching to the aftermath as elliptical shapes take over, astronomers can track the process in almost slow motion. Hubble Space Telescope images, for example, have given a front-row view of various mergers, showing star clouds several 100,000 light-years long and central knots where the action is most intense. Some galaxies have changed within a few million years, others take more than 1 billion years to really meld. All of these stories add up to a cosmic roadmap for what will eventually become of our own galactic group. Looking even further into the universe, the earliest times after the Big Bang also provide crucial hints. Here, astronomers see proto-galaxies growing by scooping up smaller clouds, merging again and again, over and over, until something like the present Milky Way emerges. That's why the process of blending, mixing, and refueling via mergers isn't just a one-time thing. It's a central driver of cosmic history, and it's also how galaxies like ours were built up in the first place. The other major thing to mention is how much this all helps fill in gaps about galaxy evolution. Observing and simulating mergers is one of the best ways to test out ideas about dark matter, how black holes affect their galaxies, and how cosmic magnetic fields interact with all that motion and energy. The more examples astronomers see, the better they can predict what sort of strange shells, clusters, or ghostly structures will show up in the result. So, the next time you see a picture of two galaxies tangled up together, it's more than just an image. It's an actual moment in the slow but unstoppable cycle of growing, shaping, and transforming the whole universe. For the local group, all this data from far-off collisions is the instruction manual for what lies ahead, as the Milky Way, Andromeda, Triangulum, and their little companions work their way through a spectacular merger that's really just the next chapter in a process that has been repeating since the dawn of the cosmos. Watching galaxies blend, collide, and reshape each other across billions of years isn't just about knowing how the night sky will look or tracking where the solar system might end up. There's a deeper level to everything scientists are working out when they study mergers like the upcoming Milky Way Andromeda Triangulum event. Each one of these cosmic stories gives us a new way to understand what kind of universe we actually live in and what it means for the past, present, and future of not just galaxies, but the kind of matter and maybe even life that can exist here. There's genuine curiosity that drives these questions, but there's also a careful, skeptical mindset. Astronomers interrogate their theories, hunt for more data, and look for the faintest details to double-check ideas about how the universe behaves. This is especially important when dealing with events that play out over such enormous time spans that you can't exactly do an experiment and wait for the answer. You have to use all the evidence possible from across the sky and try to piece together the huge puzzle. So, as researchers get more and more data on galaxy collisions and mergers, a few really big lessons are emerging, and they change the way we look at everything on a cosmic scale. One of the most obvious takeaways is how dynamic the universe really is. When people talk about space, it's easy to think of it as a quiet, empty place that barely changes. But the truth is, the bigger you zoom out, the more the universe is alive with motion and interaction. The process of the Milky Way and its neighbours drifting closer and eventually merging is just one example, out of many, showing that moving, mixing and merging is totally normal and actually necessary for how galaxies grow and evolve. No galaxy is static for long if you look at things on the right timescale. The upcoming meeting between the Milky Way, Andromeda and Triangulum really gets across the idea that change is written into the universe from top to bottom. Even the biggest, most impressive galaxies aren't around forever in their current form. They get pulled, mixed, and turned into new configurations by gravity, dark matter, and the whole set of cosmic forces in play. That means the stuff that makes up your body, your phone, and this planet, all those atoms, went through billions of years of reshaping inside old galaxies before finding their way here. The elements are blown out by supernovae, drift across space, get swept up in clouds, and eventually become part of new solar systems as those clouds collapse under gravity. If you dig further, it also becomes clear how studying one merger can shed light on seemingly unrelated objects or events. Scientists have linked the frequency of galaxy collisions and mergers with the rate of star formation. When galaxies come together, their gas gets compressed, and suddenly there are bursts, sometimes entire waves, of new star creation. This is important for a few reasons. The more stars a galaxy makes, the more planets it probably makes, and the more possible places there are for life to start. On top of that, the violence of these mergers keeps stirring up heavy elements, carbon, iron, oxygen, silicon, which are needed for building planets and, as far as we know, life. So, the cycles of growth, destruction, and renewal keep the universe lively in ways that go far beyond just shapes and locations. It's also worth mentioning how scientists use the details of mergers, like how long tidal tails stick around, how quickly black holes merge, or how gas gets distributed after a collision, as they're testing grounds for all sorts of big physics ideas. Dark matter, something that doesn't glow or block light, but exerts gravity, is best measured by looking at these large-scale motions and distributions. When two galaxies pass by each other, their stars might not interact directly, but the dark matter halos can pull and twist things, leaving behind traces you can only catch with precise measurements or computer simulations. Getting those predictions right is a huge check for the theories underlying modern astrophysics. There's also the question of cosmic time. Watching the lead-up to the Milky Way and Andromeda's merger and the fate of Triangulum, it's impossible not to realize how short human timescales are compared to the universe's rhythms. The events unfolding over 4 or 5 billion years are so far outside a human life, or even all of human civilization, that it takes special tools like astronomy, mathematics, and simulation to even think about them. Scientists approach these events with a sense of friendly skepticism. Are our predictions solid, or might we be missing something subtle, like an unknown dark matter effect, or a surprise twist in how gravity behaves at giant scales? This questioning is what drives more observations, new telescope designs, and better surveys across the sky. When you look at what all these mergers teach us about cosmic evolution, they force us to recognize that cycles are a natural pattern, not just in human life or nature on Earth, but everywhere. Galaxies are born, grow, collide, and often merge into newer and bigger galaxies. This is how the universe builds structure over billions of years. It's not a one-way process, it's a cycle of matter and energy, always in motion. Triangulum, Andromeda, and the Milky Way have all probably eaten smaller galaxies in the past and will become part of an even bigger one in the future. This helps to explain the huge diversity in galaxy types, shapes, and sizes that we see when we look out into deep space. Paying attention to mergers also reshapes what we know about how galaxies settle down and age. The big, featureless elliptical galaxies seen across the universe are often the endpoint of dozens or hundreds of past mergers. All the sharp spiral arms, gas clouds, and bright blue star clusters get smoothed together into an older, quieter stellar population. When you spot one of these huge ellipses through a telescope, you're witnessing the end result of cycles played out for billions of years. Seen this way, galaxies like the Milky Way and Triangulum are actually young by comparison, still loaded with gas and bright arms, keeping their cycles turning. There's a curiosity factor too, when astronomers connect studies of mergers with things like the distribution of exoplanets, the habits of star clusters, and the motion of satellite galaxies. These are all clues pointing to how history leaves fingerprints all over a system. Which stars have the right mix of heavy elements for planets? Which clusters are survivors from an ancient collision? If a new star-forming region pops up during a merger, does it affect the chances of new solar systems with Earth-like worlds? These are big questions that reach all the way to the search for life and the future of astronomy, giving our local group merger a more far-reaching importance than just where the Sun and solar system end up. All these insights flip the idea that change is always destructive. From a cosmic point of view, merging and mixing is what produces new opportunities. It seeds more stars, more planets, and more places for complexity. Even the danger that sometimes comes with these cycles, like close supernovae, bursts of radiation, or the rare ejection of whole solar systems, are weighed in a balance where the most likely outcome is growth. Scientists don't sugarcoat the violent beauty of a galaxy merger, but careful observation and theory show that the aftermath is usually a much bigger, richer, and more complex galaxy, ready for the next chapter in the cosmic story. Learning to read these signals, ask the right questions, and doubt your own assumptions is what gives astronomy its lasting power. Teams working on mergers use skepticism not to dismiss big claims, but to carefully test and improve models with fresh evidence. If observations don't quite fit the simulations, it's a sign to look closer. Maybe the mass is off, maybe dark matter behaves differently, or maybe the way gas cools and forms stars changes with the environment. That friendly challenge is how science grows, always questioning, always checking, and never quite taking the obvious for granted. One of the great payoffs from all this work is a new dimension to our place in the universe. Instead of seeing our galaxy as a single, isolated island, astronomy shows that we're part of an ever-changing web of interactions. Every atom in the air, every speck of dust, and every glance at the sky comes from a chain of cycles that run through galactic history. By understanding this, For the Milky Way and every other galaxy out there, astronomers can find out how rare or common certain conditions are, and maybe someday answer how life, planets, and cosmic structure all fit together. It also forms a sort of huge, living record book for the universe. Scientists track the signatures mergers leave behind, tidal streams, offset galactic centers, weird patterns in the orbits of stars and satellites, to read back in time and unravel previous collisions. As telescopes get sharper and gather more data, those cosmic fingerprints become clearer, telling a much bigger story. When you look at these clues, you see that everything in the visible universe is in motion, with every region cycling through old and new shapes, challenging the idea that anything out there is truly static or unchangeable. Mergers are also where theory and technology come together in the sharpest way. Predicting outcomes for 3 galaxies, like Milky Way, Andromeda, and Triangulum, merging over billions of years is a math and data-heavy task. It takes real measurements from telescopes, careful modelling of gravitation and dark matter, and continuous improvements as fresh observations come in from new missions. Scientists must always ask, are the computers right? Do the numbers match the subtle movements we pick up in the night sky? Could dark matter be shifting things in ways we haven't guessed yet? It's an endless loop of asking, checking, and updating as better evidence rolls in. As teams keep tracking and modelling these mergers, they also adapt their questions. What if there are wildcards, hidden black holes, clouds of gas never accounted for, or new physics waiting to be found at big scales? By pushing both their curiosity and skepticism, astronomers take cautious leaps. They expect to be surprised, and sometimes those surprises lead to breakthroughs that rewrite the textbooks. Even now, as researchers turn new telescopes toward the edges of our group, scan the patterns of stars, or listen for gravitational waves, they do so knowing the best answers are always up for review. This approach helps make astronomy accessible too. Instead of having to accept everything on faith or tradition, anyone can look at the evidence, ask questions, and see how the pieces fit. The story of galaxy mergers, when told honestly, is a process of discovery that demands checking, learning, and sometimes changing your mind when the evidence calls for it. The cycles and trends are bigger than us, but the methods for learning about them are open and real, and anybody who wants to can join in, ask their own questions, and see how the universe builds and rebuilds itself through time. So the grand drama of the Milky Way, Andromeda, and Triangulum coming together isn't only about the spectacle of cosmic fireworks or the changing night sky. Every step of the process opens new windows on physics, chemistry, and even biology, offering lessons about how stars, planets, and life itself emerge and grow. With every close study of a merger, every refined prediction, and every bit of skepticism, astronomers get a little more confident about how the universe behaves, and a little more ready for the next discovery that might change the rules all over again. To figure out all these wild shifts in the universe, the Milky Way, Andromeda, and Triangulum racing toward a collision, astronomers have to rely on some serious detective work. There's no way to watch a galactic merger from start to finish in real time, so researchers have built a kit with technology, careful measurement, and some digital wizardry to trace what's going on and predict what's next. These methods keep getting better as new tools land in observatories on the ground and satellites above our atmosphere, opening up new details and making predictions tighter with every year. At the most basic level, you start with telescopes. It used to be that astronomers were limited to what their eyes could see, so the first big discoveries about other galaxies were made just by spotting fuzzy patches in the sky. Nowadays, the toolkit includes optical telescopes that show visible light, radio dishes for tracking the coldest gas, infrared sensors to cut through dust, ultraviolet images for hot new stars, and even X-ray satellites that pick up signals from places where things are heating up fast, like when galaxies crash. The Hubble Space Telescope, which has been in orbit since 1990, totally changed the game by giving astronomers incredibly sharp views of distant galaxies, revealing new levels of detail for mergers, tidal tails, and all sorts of weird patterns that just look like blurs from the ground. But ground-based telescopes have leveled up too, with giants like those on Mauna Kea in Hawaii and in the Atacama Desert of Chile, many using adaptive optics to cancel out much of the twinkling blur caused by Earth's atmosphere. Light from galaxies holds these ancient stories, but to decode it, astronomers use techniques like spectroscopy. That's just a way to break light up into all its colours and measure how much of each colour is present. When astronomers observe the light from a galaxy and see the pattern of absorption or emission lines, the telltale barcodes unique to each element, they can tell what the galaxy is made of, how much incredibly hot gas or cold gas it holds, and even how fast it's moving relative to us thanks to the redshift or blue shift of those lines. Using these measurements, it's possible to clock the speeds at which galaxies approach or move away, or understand when big features like star formation eruptions are happening. Mapping the motion of galaxies is not just about raw speed. There's also what's called proper motion, tiny shifts in a galaxy's position on the sky over years or decades. That's a hard measurement to make when an object lies millions of light years away, but it's crucial to pinning down whether, say, the Triangulum galaxy is on a fast collision course, a near miss, or heading into orbit around the Milky Way or Andromeda. The Hubble Space Telescope has provided the kind of stable, long baseline views that actually let scientists track these slow drifts of galaxies across the heavenly grid, sometimes detecting changes as small as a few millionths of a degree every year. It's like tracking a freight train moving across the continent by measuring it a millimeter at a time. But the real breakthroughs have come thanks to digital technology that allows astronomers to make predictions using computer simulations. Once the mass, distribution of stars and especially the presence of dark matter are estimated, which they infer by watching rotation speeds and the motion of stars much further out than expected, researchers can program all these numbers into a model and run it forward or backward in simulated time. These aren't just pretty pictures, they're physics-based, guided by Newton's laws of gravity, careful tracking of angular momentum, and estimation for how gas, stars, and black holes interact. Simulations let scientists pause the universe, tweak something, like galaxy speed, angle of approach, or how much cold gas is in each system, and hit play again to see what changes. Projects like Illustris and Eagle are good examples, using supercomputers to simulate enormous chunks of the universe, showing not just single mergers, but the birth, growth, and death of galaxies and whole galaxy clusters. One tool scientists lean on a lot is the observation of gravitational waves, which are ripples in space and time caused by really massive objects speeding up or colliding. The idea itself is about 100 years old, thanks to Einstein, but it took until 2015 for the LIGO Observatory in the US to catch the first ones for real after the collision of two black holes a billion light years away. Now, LIGO and its international counterparts are on the lookout for bigger, slower gravitational waves that would signal the final spiral and merging of the supermassive black holes at the centers of the Milky Way, Andromeda, or Triangulum. While these waves are both rare and faint, catching even a few provides a check on theories, especially as mergers draw to a close. A lot of work is also done using radio astronomy. The VLA, the Very Large Array in New Mexico, and more recently, the Square Kilometre Array being built in Australia and South Africa, let research teams zero in on cold hydrogen gas, the raw ingredient for making stars. Following streams and clouds of hydrogen between merging galaxies shows where the action will be, regions likely to ignite new stars or throw out long tails and bridges that can be tracked for hundreds of millions of years. Radio maps match what simulations often predict, and when they don't, teams get to dig for what's missing or misunderstood, sometimes finding new physics behind the scenes. Because Earth's own atmosphere blocks a lot of wavelengths, putting telescopes in space is still a top priority. The James Webb Space Telescope, launched in 2021, opened up new views in infrared, looking past the dust clouds that often hide the hearts of merging galaxies from visible light. Combined with X-ray satellites like Chandra or the older Rosat, astronomers can build a layer-by-layer portrait. Hot gas, cooler star clouds, dust lanes, even the zones blasted out by feeding black holes. For galaxies on the edge of merging, finding their true distance is critical. Even tiny errors there can throw off timelines by millions of years or more. That's where methods like using Cepheid variable stars and Type Ia supernovae come into play. These stars are predictable standard candles whose brightness tells us exactly how far away they actually are. Hubble, Gaia, and more recent missions have collected database after database on these distances, so timelines for collisions are pinned down tighter than ever. On the theoretical side, cosmologists never take their simulations for granted. Every answer comes with a confidence interval that shows just how uncertain or solid the numbers are. predicting exactly when and how the Milky Way and Andromeda, or Triangulum and the others, will merge involves running the same models hundreds or thousands of times, tweaking little details, seeing which parameters drift the most, and hunting for the pattern with the best match to what's actually observed in galaxies like ours. It's slow work, but each new observation, batch of data, or sharper image gets plugged back in and new predictions come out. Machine learning and artificial intelligence have started to creep into this world too, helping to spot subtle shapes in the mishmash of stars and gas that human eyes or slower computers miss. These tools pick out the faintest tidal tails, clusters, or odd patterns in the distributions of stars, details that sometimes hold the key clue about how a merger will end or whether a new one is about to start. And it's not just about the galaxies. AI now helps teams sort through millions of images and spectra, flagging up candidates for further study and making the labor of deep surveys way more efficient. Every line of data collected, every high-resolution photo, and every simulation tells part of the story, but the real magic happens when researchers combine methods. Pairing gravimetric readings off distant clusters, timing gravitational waves, and then running a computer model that starts with data from all available telescopes makes predictions way more robust. Suddenly, it's possible to forecast not just which galaxies are closest to merging, but how the structures inside those galaxies, from spiral arms to black hole jets, will evolve during and after a collision. There's a human side to all this too. Teams of astronomers around the world have to keep standards tight, sharing data, checking each other's work, and keeping every step transparent. Open data policies mean that, with the right know-how, almost anyone can download raw readings, images, and velocity measurements and test their own model or build their own sky maps. The best discoveries sometimes come when teams share and challenge data, so honest skepticism is part of the science. As the years roll forward, newer missions keep pushing the edge. The Vera Rubin Observatory, set to begin wide-field sky surveys in the 2020s, will produce what many call astronomical movies by taking repeated snapshots of the whole visible sky. This means researchers will notice day-by-day changes, track movements of galaxies and star clusters, and maybe catch the beginnings of some future collision. That's the kind of data that lets science march at an ever quicker pace, turning real cosmic movement into something you can check against models almost as events unfold. The ability to track the actual orbits of stars inside merging galaxies also opens up new possibilities. By seeing which stars speed up, slow down, or get tossed into odd trajectories during a merger, you can cross-check against what you'd expect if dark matter is really there, and if general relativity works as predicted at these gigantic scales. When things don't match, it's a sign the models need fixing, or sometimes that new physics is lurking just out of sight. Astronomers nowadays always keep one eye on technology that will expand the toolkit. That could be better detectors for gravitational waves, next-generation X-ray or gamma-ray satellites, or maybe quantum-based sensors that catch incredibly faint cosmic signals not seen before. As these advances come online, the blend of direct observation and digital modelling only gets stronger, letting astronomers tweak, test, and recheck their predictions with more confidence. The search for understanding mergers is never just a one-shot deal. Every galaxy group and cluster is a test case. Researchers look for analogues to our own local group, a set with a few big spirals, some dwarfs swirling around, lots of gas, and all kinds of histories written in the shape and motion of the stars. Every time a new group or merger is found, the data loop grows. Sometimes, a surprising shape, a new star formation region, or even a gap in expectations pushes the team back to check every step. Maybe the distance was wrong, maybe there's a new kind of dark matter feature, or some interaction no one predicted. What all this means for the local group's future is that the best picture we can build always comes from layers. Big telescope images, radio maps, proper motion tracks, the distribution of gas, and the fingerprints of star clusters all contribute to a timeline that predicts just when the Milky Way, Triangulum, and Andromeda will come together and what the supergalaxy might look like afterwards. And every new discovery brings more surprises, maybe more neighbor galaxies that will get swept up in the merger, perhaps odd chemical fingerprints from past collisions, or a curveball in how black holes shape the story. Science, at its best, is always ready to spot the unexpected. As the field advances, astronomers hope that next-generation surveys, both from the ground and from space, will tighten the bolts on merger predictions, letting us trace where the solar system or any particular star might end up once the dust settles. Ultimately, the journey toward understanding galactic collisions isn't about reaching a final answer, but about tuning and refining predictions as technology leaps forward, bigger data pours in, and the universe keeps revealing fresh details. The curiosity, the teamwork, and the skepticism all drive a cycle that keeps uncovering what's possible, one discovery after another. In the big, changing universe, the search for the ultimate fate of our galaxy and its neighbors is bound to lead to even more interesting questions than anyone can imagine today.